Hello and welcome. This is Cambridge O-Level Physics Paper 2. The subject code is 5054. This is May-June 2020 exam, and this is the variant 1 of this examination. Let's start. Section A. In this section, it says answer all the questions and answers in the spaces provided. Okay, so question number 1, it states that figure 1.1 shows the thinking distance and the braking distance for a car being driven along a dry road and along a wet road at the same speed. So for the dry road, we are given these values. Thinking distance is 18 meters and the braking distance is 43 meters. Similarly, on the wet road, we have thinking distance as same 18 meters and the braking distance as 60 meters. Part A, it says calculate the total stopping distance for the car on the wet road. So on the wet road, the total distance, remember the total distance will be the thinking distance, that is 18 meters plus 60 meters, that is the braking distance, and overall this becomes 78 meters. So the distance is 78 meters. Part B, it says complete the sentence. The thinking distance is the distance traveled between seeing a hazard and when the brake is applied, or you can say the distance between seeing the hazard and distance traveled between seeing the hazard and application of the brakes, or you can say start of the application of brakes. So that is the thinking distance we have. Next part, it says suggest why the thinking distance is same on both roads. So the reason perhaps is that the vehicle number one is traveling at the same speed, and the driver who's driving at the same speed, the reaction time is the same for the same person. So we can say that the vehicle may be driven by the same person having same reaction time. Also, the speed of the vehicle is the same. So there are 2 points which are important here. Number one, the human reaction time, and the human reaction time is generally same if the same person is driving the car. And secondly, the speed of the vehicle is the same. So the reaction time and the speed are the 2 right answers. I mean, it's a 1-point answer. Any one of the points, if mentioned, will give you complete credit. Then part 2, it says explain why the braking distance is larger when the road is wet. So wet road actually decreases the force of friction between the wheels and the road, and when the brakes are applied, it takes more time to decelerate to zero or decelerate to lower speeds, and that results in more distance being traveled. So let's write it in words. So we can say that the wet road decreases the force of friction between the wheels and the road when the brakes are applied, uh, the car or the vehicle, you can say, takes more time to decelerate to zero or low speed, thereby resulting in more distance traveled when compared to the case of dry roads. Okay, so this is, I would say, a good answer for this question. Okay, next part. Question number 2. It says the student performs an experiment to mark the center of mass C on a thin piece of card. There are two holes in the card. Figure 2.1 shows the card and two lines that student draws on the card. So these are the lines which are drawn. These are the two holes. Let's say we call this hole A and we call this hole B. So describe a method used to draw these two lines in their correct positions on the card. Make clear what extra apparatus is needed. You may draw a diagram if you wish. Okay, so it's a very simple question, and that has been a part of the alternate to practical exams in many of the previous exams. So what extra apparatus we need? So remember, apparatus, uh, we need a clamp, but to needle slash pin. Number 3, stand, and number 4, uh, plumb line. So we need these things. So if you are going to draw a diagram, so consider it's something like this. So this is our stand, this is the clamp that is associated, and this is the needle and the pin. And this is say we have suspended the box from this hole. Say for example, this is the card, this is my pin, this is clamp, this is my stand, and this is the plumb line that is, for example, associated with it. So plumb line, this is the plumb line that is associated with something like this, a rough figure. So I would say excuse my bad drawing, but something like this would be a good design or a drawing to show what exactly is happening. So we can call this as A, this as B. So, and even if you're not going to draw this, this is fine. If you're just mentioning what exactly the apparatus you are using, and you're using explaining it correctly in words, that would be fine for your answer. So let's write. First of all, we need a clamp, pin, in the clamp, a pin, a stand, and a plumb line to measure, or you can say to locate, or to determine, not measure basically, so to determine the center of mass C. Okay. First of all, suspend the card from point A along the pin and wait till it comes to rest, or basically reaches its equilibrium state, so as shown in the figure. Okay, one part. Then uh, part two. So then suspend this thumb plumb line. Suspend the plumb line from point A and mark the line on the card corresponding to the plumb line. Okay, then repeat the procedure for the point B. The two lines intersect at point C, which is the center of mass of the card. Okay, so we can explain this whole phenomena in this fashion, and I mean you're free to use your own choice of words to explain this. Okay, so next part B, it says the student holds the card loosely between her fingers. The card is vertical, resting with its lower edge on the bench as shown in figure 2.2. The card is slightly tilted, so the card is tilted slightly as shown and then released. Okay, so the card is tilted right and then it is released. Okay, when the angle, it says when the angle theta is small, the card falls clockwise back to its original position. Explain why the card falls anti-clockwise when theta is large. So see what is happening. So if the card is at rest, the whole weight is acting downwards. So this is the weight of the card and it is acting downwards. Say call this A, B, C is here, D, E, and F. So let me label it for you so that will become easier in explaining this. D, E, and F. The whole weight is going down, is acting downwards on this line. So as long as this weight vector is passing through this line AB, irrespective of this angle, how much you tilt, this card will fall back to this baseline AB. But when the theta this theta angle becomes greater such that this vector does not pass through this line AB, this card will tilt, and if theta is large enough, what will happen that this vector will eventually pass through, or the center of mass will start passing through AF line, or the baseline AF. So as this weight vector starts to pass through line AF, the moment will be generated across this pivot point, and the card will rotate anti-clockwise and stabilizes on base AF. Now, this is what happens. So let's try to write it. So we can say that when theta is large, the weight acting downwards will, or the weight vector acting downwards will not pass through the baseline AB. Instead, it will pass through the line marked AF on the figure. This will cause a moment about point A, and you can say it will cause a moment around point A, which results in anti-clockwise rotation of the card. The card then settles on the baseline AF. Okay, so this is how it happens. So the card falls falls and settles on the baseline AF, and that moment is generated across point A, and because of the weight vector that is acting downwards. Then it says part 2, it says state 1 change to the card that makes it more stable. So if we are going to increase the base line, that will lower the center of gravity, and that will cause the card more stable. So increase in the length of the baseline, for example AB, will lower the center of gravity of the card, thus making it more stable. So in this case, basically what happens is that once the length of line is increased, you need much higher angles or theta in order to rotate this card anti-clockwise or clockwise, depending upon on the force, because the force vector will be acting on a larger or the force vector will be acting on a longer length as compared to earlier. Okay, so next part, question number 3. Next is question number 3. It says student suspends a spring from a support. He attached different loads to the lower end of the spring. For each load attached, he measures the extension of the spring. So figure 3.1 shows the extension load graph obtained. So here what we see on the y-axis, we have extension in centimeter on the load, and on the x-axis, we have the load in newtons. Part A, the question, it says, the extension of the spring is directly proportional to the load. State two features of the graph that shows this. So the graph basically shows that the extension, so let me call this x, is directly proportional to load. So x is directly proportional to F. Okay, so x is k times F. So from the graph, we can see that the graph number one passes through origin. It means that this graph is proportional. The second thing, we see that this graph is a straight line, and the slope of this straight line is constant. So these are the two features we can say. So we can write the graph is a straight line with a constant slope. Second thing, the graph passes through the origin 0 0. Okay, so any graph passing through origin, this is one of the measures or one of the features to show that there is some proportionality constant or proportionality relationship between the two variables. Okay, then it says part B, describe how the student can show that the spring reaches its limits of proportionality at 8 newtons. So this is how student can say, let's write it. So increase the load beyond 8 newtons by, let's say, by x newton, and measure the extension, say y centimeter. Now calculate the slope. So, and good way is to just use this graph. So we call this, say, point A, and say if I have added an extra load, so this is 8 plus x newtons, and this is at this is point B, so x is 8 plus x, and my extension is y. So this is the point which we are, or which is achieved. So calculate the slope of AB bracket as shown on the graph, and that slope is delta y by delta x. That can be given as say y minus 6 divided by x, you can say it is x, let's see, x, yes, okay. So y minus 6 divided by x. Okay, so this is the change in yeah, you can say extension, and this is the change in y. So if the value of the slope is not equal to uh, the equal to the sorry, slope of the line OA, that is, so let's see what is the slope of lines. This is my point O and A. So slope OA, slope OA is, say for example, change in Y by change in X. So delta Y 6 divided by 8, so 3 by 4. So the slope that is equal to 3 by 4. You can say that the, if not equal to the spring has reached its limit of proportionality. Okay, so just do something like this. So increase the load, say by X Newton, and measure the extension, and say that the new extension is Y centimeter. So calculate the slope of AB, and if it comes out to be delta Y by delta X, so change in Y, so Y minus 6 divided by X. If the value of the slope is not equal to the slope of the line OA, that is 3 by 4, the spring has reached its limit of proportionality. Okay, it's very simple now. Next part, question number 3, part C. It says the spring is used in a simple device known as accelerometer. So here is the device. So we have the spring is fixed at one end to a mass. So we have mass equals to 5 kg. At 5 kg at the other end, the rest, the mass rests on a smooth horizontal surface. There is no friction between mass and the surface. The whole car, the whole device is placed in a car. The car accelerates, and the student noticed the extension in the spring is 3 centimeters. So X is 3 centimeters. Okay, find the acceleration of the car. So we have seen that X is equal to K times F, where K is the slope. So K equals to X by F. So X is from the slope, this comes out to be 3 by 4, and this is centimeter Newton. So this is my slope. And then what we have to find out the force here. So force is equal to X divided by K. So X is 3 centimeter divided by 3 multiplied by 4. So the force is 4 Newton. Again, for acceleration, we know that force equals to mass times acceleration. This gives us acceleration is equal to force divided by mass. So acceleration comes out to be force as 4, mass is 5. So meters per second square, and this is 0.8 meters per second square. So answer is 0.8 meters per second square. Okay, so this is how you calculate this answer. Next part. So question number 4, it says glass and glass and iron are good conductors of heat. However, glass is a poor conductor of heat and iron is a good conductor of heat. Okay, describe using the ideas about particles how the conduction of heat takes place in glass and iron. You should make it clear why iron is a better conductor of heat. Okay, so remember that one is so iron is a metal, so metals are generally good conductors of heat. Glass is you could say it's not an it's an amorphous sort of material. Um, so it's a, you can say, non-metal, but generally how heating takes place. So in glass we have the molecules of silicon oxide, generally the material on which the glass is made, and they are they've not a very a good latest structure of glass. So once they start, when we heat these molecules, so these molecules start vibrating on the heated end, and they transfer these vibration to their adjacent molecules, and from and since they transfer these vibrations, they start vibrating more vigorously, and since the more the vibrations, more will be the collisions between them, and more will be the increase in temperature, and that is how the overall temperature transfers from one end to the other end. Whereas in metals, what happens is that apart from these so we have very well defined structure of atoms in metals, so and along with them we have the free electrons. So once heating starts to take place, these free electrons start vibrating vigorously, and these metals, these atoms also start vibrating vigorously, and there is these free electrons which on whose movement or vibrations which are allowed to freely move through the latest structure of metals, they add to the manner in which it becomes a much better conductor of heat. So let's try to write these points down in words. So conduction in glass. So um, how we can write it? So let's say heating the glass increase the temperature of the molecules uh, the increase in temperature increases the average I would say kinetic energy. Let's me write it K of the molecules, making them making them vibrate more vigorously. Uh, the increased vibrations uh, results in transfer of energy from uh, one so uh, from the region of higher temperature to uh, to lower from the region of higher temperature to the lower temperature, thereby conducting heat. Okay, so this is how overall conduction takes place in glass. And in case of iron, so heating of iron heating of iron results in increased kinetic energy of the atoms and free electrons In some cases, you can also call them ions as well. So free electrons is a better word than ions. Um, Present near the hotter end. Okay. Uh, these so the atoms start to vibrate more vigorously, transferring more vigorously, uh, so more vigorously, and uh, the free electrons. So basically, both atoms and free electrons gain energy and start to vibrate. Atom starts to vibrate more energy, and the free electrons gain. Um, so we have maybe, so how can I write it? So the atoms start to vibrate more vigorously, transferring the energy to the nearby atoms, whereas the free electron collisions with the atoms also increases. This results in much faster, uh, let's say, transfer of energy, or bracket may we can say temperature, faster transfer of energy from from hotter end to the cooler end, thereby uh, uh, the you can say the material conducts or metals conducts much better manner uh, compared to the non-metals such as glass. Okay, so this is how you can write in terms of uh, the particles. For example, in glass we are more concerned with the molecules, whereas in metals the key difference lies because of the free electrons and the lattice structure of the, or a predefined lattice structure of the atoms which are available in the metals. So this is how you can easily write this answer. Then part B of this question, it says figure 4.1 shows an apparatus used to show expansion. First of all, the flask or the glass flask full of water is heated. A student is surprised when the liquid X in the glass tube falls for a few seconds before it rises. So just why the liquid falls and why it then rises. So basically what happens is that when you're heating this flask, so this flask is made up of glass, and that glass expands on heating. So when the glass expands on heating, the overall volume increases. So when the overall volume increases, this liquid will fall for a brief moment. And once the glass is expanded to its limits, the water starts to heat up inside the glass. Uh, and once the water starts to heat up in the glass, the water expands, and then the liquid starts rising again. So this is how what it happens. So you can write it, uh, the the glass expands when heated. This causes increase in volume of the flask. Therefore, uh, volume of the flask causes increase in volume of the flask, making the liquid level to fall initially. Okay. Uh, Once you can say after some time the water starts to heat up. You can say after some time the water inside the flask gets heated and expands. This causes the liquid level to rise. Okay, so this causes the liquid level to rise. Okay, this is how you explain this phenomena. Okay, then part 2, it says describe how heat is transferred throughout the water in a glass flask. So remember what is happening. So this is the glass flask. uh, this is here. So we are heating from this end. So the convection currents are developing inside the water, and this convection current is um, how uh, you can say uh, the heat is transferred from the hotter end to the upper or the cooler end in the water. And let's explain this. So again, remember, heat is transferred throughout the water. So basically it's not asking about the heat transfer in this glass material. It's all asking about this water, and that water is a liquid. So the water at the bottom of the flask heats up, making it less dense. This makes the warm water at the bottom to rise up, and cold water, or we can say denser water from the surroundings comes and takes its place. This process starts a convection current inside the flask. This convection current then heats up the, or or you can say this convection current then transfers. This convection results in transfer of heat throughout the water in the flask. So this is how you explain this. So the heating makes the water close to the heating element less dense, and that less dense water rises in, resulting in the cold water from the surroundings coming and taking its place, and this actually sets up a convection current, and this convection current results in transfer of heat throughout the water in the flask. Okay, next question, question 5. It says, part A, use the relationship between pressure, force, and area to explain why it is harder to cut something with a blunt knife than a sharper knife. So remember, pressure is given as force per unit area. The blunt knife presents more area compared to a sharp knife, resulting in less. So remember, pressure, force per unit area, in less pressure applied on a surface for our surface compared to a sharp knife for same amount of force applied. Okay, so this is how we can say that, and this thus again, that is fine. I mean, it is up to us. So, or you can just use your own words to explain this phenomena. Remember, pressure is force per unit area. So blunt knife presents more surface area compared to a sharp knife, and this results in less pressure applied on a surface compared to a sharp knife for same amount of force applied, thus making cutting difficult. Okay. Then part B, it says experimental measurements on gas pressures were made by Robert Boyle. he showed P1 V1 equals to P2 V2, where P1 and P2 are the initial and final pressures of gas, and V1 and V2 are the initial and final volumes of the gas. State two quantities that must remain constant when this equation is used. So first constant quantity is the temperature of the gas. So temperature of the gas. The second quantity is mass of the gas, mass, or you can say in some case number of molecules of the gas. So I mean, these two should remain constant. Okay. Next part, it says figure 5.1 shows the molecules of gas as the volume of gas is halved. So this is, for example, the area, and or in the volume that is fixed. So the volume is halved. And the equation we're using is P1 V1 equals to P2 V2. Okay. The equation suggests that when the volume of gas is halved, the pressure doubles. Using ideas about molecules, explain why this happens. And so remember, pressure equals to force per unit area. So molecules are colliding with the walls of the container, and if the molecules are compressed, the area of the container is reduced, and number of collisions per unit area will increase, thereby increasing the pressure exerted on the gas. So using the molecules, we can say that this question suggests the volume. Say the effective area available to the molecules decreases. This results in more, so this results in increased pressure as pressure is force per unit area. So in the so here the pressure, we can say the pressure is doubling, the volume is halved. So effective area available to the molecule decreases. This results in increased pressure as pressure is force per unit area. Thus, or you can say that thus the pressure or in terms of molecules. So what in terms of molecules? So we have number of molecules in both. So we have 10 molecules here. So we can see 10 molecules here. So the walls or the areas or the number of molecules striking these walls. So the number of molecules striking these walls again are this. So but the frequency of collision, you can say, because generally if temperature increase, the molecules, the collision frequency increases. So that is actually not happening here. So we are not supposed to use those words which basically convey a meaning that gives a feeling that the temperature is increased. So we have to stay in this sort of thing that since the area is reduced, the molecules colliding with a much lesser area will, or with the same force, much lesser area will result in more pressure. So this results, the molecule decreases. This results in increased pressure as pressure force per unit area. Effective area available to molecules decreases. So the molecule striking the wall, molecule decreases. This, yeah, I mean, this is uh, uh, I would say it's a fine answer. It is enough. So they are also saying that the pressure doubles. So I mean the area, or you can say that the volume reduced. I mean, this is fine. I mean, I will go with this answer. I mean, this is fine enough. The 2 points are much clearly explained. So the area available to molecule decreases, and if area decreases, the you can say the pressure increases. Okay. Then question number 6, it says a dentist uses a plane mirror to see the back of a tooth. The plane mirror produces an image on the object. Describe the position of the image. So this is how it looks like. So this is a plane mirror. There is a tooth, and the doctor is seeing this tooth. Okay. So the image found by a plane mirror, remember, it is so it says describe the position of this image, and we know that the image formed by the plane mirror is number 1, same as it is at the same distance inside the image, inside the mirror as it is outside the mirror, and you can say almost equal in size. But so let's see, let's write it out. So this is for 2 points, so we have to basically give 2 properties. And so you can say the image appears behind the mirror, and at the same distance as the object is in front of the mirror. Okay. So this basically is related to the position of the image. So it's not talking about the size or the size of the image, or the nature of the image. So that we're talking. So behind the mirror, and at the same distance as the object is in front of the image. So this is the 2 points which are important here: behind the mirror and same distance as the object in front of the mirror. So this will give you complete 2 credit. I don't see any reason why this thing will not be considered a good answer. Okay. Then part B, it says figure 6.1 shows a plane mirror used by the dentist to see the point labeled X on the tooth. On the figure, mark the position of image X found by the mirror. So we have to find out the position. So first case, I mean, use a ruler and make sure and extend this a little further. So the best way is to draw a ray like this and draw a ray like this. Use a ruler, make sure that this angle is theta1. So you are basically seeing here. So theta1 is here, theta r is here. So you are looking in this, so the reflected ray goes like this. Position of the image, so this image will be this, and extend this ray like this, and extend this ray like this. So this will be your position of image. So remember, this distance d1 is equal to this distance d2. d1 equals to d2, and this is something which we have written in the previous point. So this is the point where your image will be. Okay, part one. Then draw the ray of light from X to show the dentist can see the tooth. So ray of light from X. So instead of arrow this, so the ray of light will be, we'll be using the arrow like this. So this is the ray of light from X. Angle of theta I incidence is equal to angle of reflection. So this is the reflected ray going into the light. So let me draw it more clearly. So this is how it is going. So this is theta r. This is how it is. So draw a ray of light from X to show how. So the ray of light. So remember, in this case, theta I is equal to theta r, and this is for 2 points. So they are basically looking for this, that you know the laws of reflection from a plane mirror. Okay. Then part C, it says one characteristic of the image found by the plane mirror other than its position. So we have talked about the position. So other than that, I mean, image is equal in size of the object, and also the image is virtual, or we can call it as laterally inverted. Okay, so this is a virtual image or a laterally inverted image. Okay, so these are any one of the properties. I'll go with the equal in size of the object because it is easier to remember for anyone. Okay, so next part, question number 7. It says isotopes of carbon are carbon 12 and carbon 14. One of the isotopes, carbon 14, undergoes a radioactive decay. So what? So describe what is meant by radioactive decay. So radioactive decay is basically the emission of one or more radioactive particles such as alpha, beta, and gamma from the nucleus of the atom. Or so just write it like this. So radioactivity, or so radioactive decay is the emission of one or more particles of one or more particles, and that is alpha, beta, and gamma from the nucleus of an atom. Okay, so this is emission, and this emission can be random emission as well. So emission of one or more particles, or those that is alpha particles, beta particles, and gamma particles from the nucleus of an atom, that corresponds to a radioactive decay. Then part B, it says carbon 12 has a proton number or atomic number of 6 and a nucleon number or a mass number of 12. Complete the table 7.1 for neutral atom for each of these two isotopes. Remember, when the isotopes are same number of protons but different number of neutrons. Okay, so same number of protons, so same number of protons, and number of protons are always equal to number of electrons. So 6 here, 6 here, and 6 here, and different number of neutrons. So this is carbon 12, so 6 minus, so neutron will be sum of, or the the nucleon number will be the will consist of protons and neutrons. So if the nucleon number is 12, Oh, sorry, if the yes, so nucleon number is 12, so it means that there are 6 protons, there will be 6 neutrons. Similarly, if the nucleon number is 14, so there is 6 protons, and then there will be 14 minus 6. This is basically 14 minus 6, and this is basically 12 minus 6. So this comes out to be 8. Okay, so this is how you complete this table. Then part C, it says a sample of carbon 14 is contained in thin aluminum container of 0.2 millimeters. Radiation from the sample is detected outside the container. When the thickness of aluminum is increased to 6 millimeter, no radiation of the sample is detected outside the container. State the type of radiation which is stopped by increasing the thickness of aluminum. So remember, alpha particles are stopped with just a simple sheet of paper. So this is a 0.2 millimeter thick aluminum container, and we have to increase the aluminum container's thickness. So alpha particles are definitely not here. For gamma particles, we need lead coating. And so we are basically talking about beta particles here. So initially, 0.2 millimeter thickness was giving us, um, you can say, some uh, radiation or some detection outside the container. It means that for sure alpha particles would have been blocked by the uh, container or by the 0.2 millimeter thick aluminum. And if you are getting the radiation, it means that it can be either beta or uh, uh, or gamma. But after increasing it to 6 millimeter, we do not have any radiation. So it means that we are only talking about beta particles here. So the answer is beta particles. So if there would have been gamma particles, after 0.6 millimeter, we should be getting some sort of radiation. Okay, then it says explain how do you know the sample does not emit one other type of radiation. So uh, just explain what I have told earlier. So let's say once the thickness of aluminum is increased to 6 millimeter, there was no observation of radiation. Okay, so there was no observation of radiation in a case of radiation. It means that the sample was emitting alpha and beta particles, both of which can be stopped by 6 millimeter of aluminum. So I'll call this aluminum Al. Uh, in case of the gamma particles, both of which can be stopped. So in case of presence of gamma particles, there should be radiation detected after 6 millimeter of aluminum, because lead covering or lead coating, you can say, is required to stop the gamma particles. So therefore, I mean, you can easily pass through aluminum sheet. So there should be some radiation because they can easily pass through radiation, or you can say lead coating is required to. I mean, just instead of lead coating, you can say because direction actually because gamma particles can easily pass through lead as well. So, oh, sorry, pass through 6 millimeter of aluminum. So that is basically the key reason for it. So moving on ahead. So next is our section number B. So in section number B, we are technically asked to answer 2 questions out of 3, but again, I'm solving it for all of you. So I'll be answering all 3 to the best of my abilities. So let's start. So answer any 2 of the questions, answer in the space provided. Question number 8, it says, figure 8.1 shows a lamp from a car. It contains 2 metal filaments. Complete the boxes to describe the transfer of energy that takes place when the lamp is switched on. So basically, energy, initial input energy is electrical energy, and that electrical energy is converted to heat, heating of the filament, and light energy that is seen by us. Then part 2, it says the efficiency of a filament is less than 10%. State what is meant by the efficiency. So efficiency is, remember, so efficiency is energy output, or the useful energy output over useful energy input into 100. Okay, so it is the ratio, again, in percentage of the useful energy uh, uh, output to the to the total energy at the input. Okay, so this is how or we can write what is meant by the efficiency. Then part B, it says 2 filaments are usually connected in parallel to a battery. The student investigate what happens when the filament are connected in series rather than in parallel. He uses the same battery for investigation. So we have the same battery. State whether the current, voltage across each filament and the total power produced increases, decreases, or stays the same when the 2 filaments are connected in series. So we have to basically compare them with respect to parallel. So for example, these are our 2 lamps, and they are in parallel. So these 2 lamps are in parallel and they are connected to a battery. Okay, so let's say this is the battery V and this is the current I, this resistance, and assuming that both of the resistances are same. Let's for the sake of simplicity I'm talking. So what will be the current? So current in this branch will be V by R, and in this branch will be V by R. So the total current I total will be 2 times V by R. Okay, so this is and my power will be VI. V is, so I is 2, so 2 times V square by R. So this will be the total power that we will be getting over here, or that will be used. But when it is connected in series, so see what will happen. So this, So this is, for example, the series. So this, say, assuming again the resistances are same, the current I is going out. So this, so voltage is the same. So so the current that goes through is I divided by V over 2 times R. So this is the current that is flowing through this, and my power. So this is in parallel. The power in series will be again VI. So my voltage is V. V divided I is 2R. So V square by 2R will be my uh, I. Or just if I have to say not VI, it would be I square times R. Will be the power absorbed, again I square times uh, PI power supplied. Yes, that, I mean, that is fine. So so my power basically decreases. So power is decreases. My voltage again state whether current voltage across each. So what this is not, this is voltage across each filament. So here we have voltage V appearing across each filament, and here we have voltage that is V by 2 and V by 2. So voltage across each filament also decreases. Okay, and current across each filament. So current was V by R. Both of these filaments have V by R current going, but whereas current is same in this, so V by 2 R. So basically the current also decreases. So all of these three uh, values we have, or we can say that the current, voltage, and power has decreased in case of series connection of these two filaments together. Okay, then part C, it says the figure 8.2. So 8.2 is the figure is shown. This is the current and voltage graph of the filaments. So it says shows the current and voltage graph of the two filaments. Okay, so this is the graph we have. So it says calculate the total resistance of two filaments when they're connected to a voltage of 12 volts. So for, say, let's call this as filament 1, and let's call this as filament 2. So for filament 1 we have current of 2 amperes at 12, and for filament 2 we have current of 0.5 at 12 volts. So let's say for filament 1 my value of current is 2 ohms, sorry, 2 amperes. My voltage is 12 volts. So resistance using Ohm's law, V by I, this is 6 ohms. Similarly, for filament number 2, my current is 0.5 amperes. My voltage is 12 volts. Resistance value V by I. So resistance comes out to be 24 ohms. Okay. So this is R2, this is R1. So again, a total resistance of the two filaments. So the filaments are in parallel. Okay, so remember, for parallel, R total is equal to 1 by R1 plus 1 by R2. And this thing can be written as RT, R1, R2 divided by R1 plus R2. So putting in the values, 6 into 24 divided by 24 plus 6. Okay, and this value, R total, comes out to be 4.8 ohms. So my overall resistance in parallel for both of these filaments according to the graph is 4.8 ohms. Okay, then part 2, two filaments are made up from same type of metal and have same length when uncoiled. They both operate at same temperature. So just why one filament has a resistance greater than the other? Interesting. So remember, resistance is equal to rho times L over A. So we have made up of same material operating at same temperature. They have same lengths, but it is a possibility that the cross-sectional area of one of the filaments is smaller than the other. So the cross-sectional area of the two filaments is different. Okay. Uh, the one with smaller area will have more resistance. Okay, this is how you write this answer. Okay, next part, part D. Part D, it says figure 8.3 shows a relay used to switch on the car headlamp. Explain why headlamp heat lights up when the switch S is closed. So this is the circuit. So when switch S is closed, the current flows through this magnetic or through this relay. Um, so the current is flowing. So this is the positive part. So the positive is going here. So positive goes here, something like this. Positive goes here. So according to, so the current flows through this coil and this iron core. So it basically makes it an electromagnet. And when this makes it an electromagnet, so if I use the right hand rule, the curve, the curls or the fingers, the curled fingers point towards the direction of the current, and the thumb points towards the direction or the north of the magnetic field. So north is here, south is here. So this south pole of this electromagnet induces a north pole over this armature core at this point, and this basically attracts it to this point. So this attracts it there. So this is the pivot point. A moment is generated and this armature moves in this direction. And when this armature moves in this direction, it basically closes these two, this flexible contacts, and then these flexible contacts are closed. This circuit is complete, and headlights, when current starts flowing through the headlight, resulting in lighting up the lamp. Okay, so let's try to explain this thing in words. So okay, so when the switch S is closed, the current flows through the coil and iron core, making it an electromagnet. Electromagnet. Uh, the electromagnet induces opposite pole at the shorter arm of the iron armature, thereby attracting the armature. This results in moment generated across the pivot, which in turn moves the longer arm of the armature, comma, closing the flexible contacts, closing the flexible. Thus, the circuit of headlight H is complete and the light turns on. Okay, so you can write this whole story in this fashion. Again, I mean, I'm pretty confident that all of you are much better writers than me when you have to write this thing in terms. So again, revising this whole stuff. So what or the things you have to remember to have or to get these 4 points for you. Number 1, the current flows and the making of this electromagnet. Number 1. Number 2, induction of opposite poles to the iron armature. Number 3, generation of moment across this pivot. And number 4, the moment closing the flexible contacts and completion of this circuit for the headlight and the headlight turning on. Okay, so these are technically the 4 points which the examiners will be looking forward from all of you to have or to make sure that you all understand this concept properly. Okay, next question number 9, it says ultrasound and X-rays are both used in medical imaging. Define what is meant by ultrasound. So ultrasound, again, ultrasound uh, are sound waves above the 20 kilohertz, uh, above the 20 kilohertz frequency, which cannot be heard by human ears. Okay, uh, so this is I would say how we can define ultrasound. Then part 2, describe what happens to ultrasound waves as they meet boundary between two different materials. So the ultrasound waves are reflected and refracted at the boundary of two different materials. Some of the energy is also absorbed by the materials. Okay, so these are you can say that the way in which uh, waves travel, or whenever there is a discontinuity of one medium to another, Or, and again, you can also draw a diagram like this. You can say medium 2, this is medium 1. So a sound wave coming like this strikes and reflects back again, something like this, and it, depending upon which the density of the medium, it either moves away from the normal or towards the normal. So some of the wave goes like this, but and some of the energy of these waves is absorbed in the materials as well. Okay. Next, part 3, it says to produce an image of an unborn child, an ultrasound emitter and receiver are placed close together on the mother's skin. Figure 9.1 shows pulses detected by the receiver. So pulse A is emitted and pulse B is the first pulse that returns from the unborn child. The average speed of sound in human tissue is 1500 meters per second. Calculate the distance between the emitter and the child. So remember, the time difference between the pulses, time is, this is 0.05 milliseconds. This is very important. Do not forget the units, and this is 0.02 milliseconds. So time is 0.03 milliseconds. So remember, so this is the skin, and here is, say for example, the unborn child. This is the skin. So we have this emitter and this is receiver. So the sound wave goes this and are received. So assuming that the distance traveled is 2 times d. So this distance will be 2 times d. Velocity is given to us and time is also given to us. So distance is equal to velocity into time. So the distance we have to find out. And velocity is 1500 multiplied by 0.03 milli. So, and remember this distance is 2 times d. So this is actually 2d. And d will become 1500 multiplied by 0.03 just divided by 2. I will call it at d dash. So d dash. So d is 22.5 millimeters, or you can say d is 0.0225 meters. Okay, so any of these two will be fine. So 22.5 millimeter is equal to 0.0225 meters. Okay, so you just do this calculation in this manner and you will be perfectly fine. Then it says the speed of ultrasound in human tissue is close to the speed of sound in water. Okay, suggest the approximate values of speed of sound in solids and gases. So remember, speed of sound in gases, or for example in air, here it is around 300 meters per second, or generally a good range. If you have to write a range of values, anything between say 150 to say 1000 meters per second will be a good value. So okay, just remember the speed of sound in air is something 330 meters per second, so that is fine. So in solids, so again in solid the range is generally 2000 to say around about 10,000. So just a safe is 8,000 is good according to your marking scheme. So something around 5,000 meters per second would be a good answer to that. Okay. Uh, uh, or generally rule of thumb for that, or a good rule of thumb, speed in air, generally 300 meters per second. Speed in water is multiplied by 5, and speed in ground or is multiplied by 15. speed of air. Okay, so this is a general rule of thumb. So if whenever you are asked, so compare, you can compare this value with solids, you can compare this value with liquids, and this is with gases. Okay, so generally whenever you're asked, keep this rule of thumb in mind. Always remember speed of sound in air as 300. Generally it's around 330, and then just move ahead with these values. Then part B, it says figure 9.2 shows an X-ray image of a hand. An X-ray detector is placed just above the hand. The image of the bones and human tissues around the bones is formed on a screen by the detector. Okay. Part A, describe what happens to the X-ray uh, to produce the image. So basically what happens is that X-rays are electromagnetic radiations. They pass through an object, and depending upon the density of the object, they are either absorbed or they just simply go through it. Since the whitish part is the bones, and they are the the most dense part in this image or a human body. So you can see that most of the X-rays are absorbed in the bone. Then there is contour around the bones. That contour basically shows the muscles and the tissues, human tissue that is much less dense, so less X-rays are absorbed there. And then we see the black screen, and that is the photographic plate on which the X-rays are falling. And technically where the black region is actually the region there is no interference with the X-rays. The X-rays is just simply falling on the black. And that is what is happening to the X-rays when and how they are producing this image. So let's write it down. So X-rays are electromagnetic radiations uh, which are absorbed by an object based on its density. Uh, the black region is the region where there is nothing present, uh, and the X-rays fall directly on the photo plate. The solid white lines are bones which absorb most of the X-rays. The contours around the solid white lines are the tissues and muscles. Uh-oh. Which partially absorb the X-rays. Okay, so this is how the image is produced. So we have a photo plate behind. So X-rays are coming from the top, and wherever there is nothing present in between, so we are getting a dark image, and wherever there is something present, the image is formed based on its density. Okay, so then question number 2, or part 2 of this question. So it says the wavelength of X-rays used is 2 into 10 to power 9. The speed of electromagnetic waves is this, 3 into 10 to power 8 meters per second. That was the frequency. So remember, C equals to F lambda. So we have to find out F equals to C by lambda. So C is 3 into 10 to power 8. Lambda is 2 into 10 to power minus 9. So this comes out to be 1.5 into 10 to power 17, and the units are hertz. Okay, so frequency of 1.5 into 10 to power 17 hertz. Okay, so this is the X how it goes. Then suggest one reason why X-rays are not used to form an image of an unborn child. So X-rays are basically ionizing radiations. So this is, and it can destroy human cells. So let's round up. Uh, X-rays are radiations that destroys human cells. Uh, Long exposures can cause mutations and cancer. Um, this is dangerous for an unborn child. Okay, so this is very dangerous for an unborn child. So that is the reason why these X-rays are not used, and instead of the X-rays, ultrasound waves are used to monitor the unborn child or the fetals. Okay, so next question, question number 10. It says figure 10.1 shows a motor lifting a mass. Figure 10.2 shows the circuit diagram of connections to the motor. Part A. The current in the motor is 1.5 amperes. The voltage supplied by the battery is 8 volt. Okay. So number 1, complete the circuit diagram in figure 10.2. Show the ammeter and voltmeter in correct position to take these measurements while motor is working. So remember, current in the motor. So if we have to measure the current in the motor, and we have to measure the voltage supplied by the battery. Okay, so voltage supplied by the battery. So if we have to measure these voltage supply by the battery, so supply by the battery is that we have to connect the voltmeter in parallel across the battery, and we have to measure the current through the motor. So ammeter comes in series through the motor. So ammeter comes here, the voltmeter here. Remember, ammeter comes in series, the voltmeter comes in parallel uh, against uh, whatever the device we want to measure the voltage. So if, for example, I'm talking about an example, if you have to find out the voltage of motor, our voltmeter would be connected something like this, Vm. Okay, but this is since not the part of the this question, I'm just talking it as a concept, or in case we have to find out the motor. So here we are talking about supply of battery. Okay, so if we have to measure these values, current in the motor and the voltage supplied by the battery, we have to connect these. So then it says the motor takes 4 seconds to lift the mass. Calculate the electrical energy. So electrical energy is power multiplied by time. Power is VI, volt into I, and time is T, seconds. So voltage is 8 multiplied by 1.5 multiplied by 4 seconds, and this answer comes out to be 48 joules. Okay, so energy is 48 joules. Okay. Next part. It says the motor lifts 150 grams mass through a height of 80 centimeter in 4 seconds. Calculate the gravitational potential energy gained by the mass. The gravitational field strength is this 10 Newton per. So remember, gravitational potential energy is given as mgh, where mass is given in kgs. Okay, so mass is 150 grams divided by 1000 is the mass in kgs, multiply by 10 Newton per kg. The gravitational force strength, remember this is in kg, multiply by height is 80 centimeter. Remember the height is always given in meters. So height in meters. So this eventually comes out to be potential energy 1.2 Newton meters, or this is 1.2 joules. Okay, so the gravitational potential energy 1.2 joules. Okay, state two reasons why the gravitational potential energy gained by the mass is less than electrical energy supplied by the motor. So remember, the electrical energy supplied by motor is 48 joules, whereas the gravitational potential energy is 1.2. So we can in the motor some energy is lost in the heat uh, in the motor, because the motor have some electrical winding and there is some I square R losses going on, and that I square R losses also produce some heat. So that is the heat that is there, and some energy is converted to the kinetic energy of the motor. So since the motor is rotating, the rotating shaft is also having a certain velocity and certain mass, and some of this energy is converted to kinetic energy of the motor. Okay, so these two are the very valid reasons for such an answer. Then part B, it says figure 10.3 shows a structure of a motor. So we have a structure of the motor. So it says when the mass reaches the top of its motion, the switch is open. This disconnects the battery and causes the mass to fall. The coil turns as the mass falls. Okay. As the coil turns, a small voltage is produced. Explain why the voltage is produced as the coil turns. So this mass is basically they are talking about these commutator rings or this mass. So as this mass turns, at stop of this motion, it disconnects between A and B and F. So it says explain why the voltage is produced as the coil turns. So remember that this is a conductor, or this is so as basically this conductor is moving, this is cutting the magnetic field lines that are between the north and the south pole. So since the cutting of the magnetic field lines changes the flux, and that change in flux induces EMF in this conductor, and that EMF is in the opposite direction, and that is because of the Faraday's laws of electromagnetic induction. Okay, so we have to write this thing. So let's see the rotation of the coil cuts the magnetic field lines, causing a change in magnetic flux across the coil, and that coil is the conductor. Okay, the change in flux produces electromotive force EMF that opposes the cause producing it. Oh, sorry, change in flux induces electromotive force. That's the electromagnetic law of induction. So the right word is induces electromotive force. Uh, Opposing, the good word is opposing. So because it is minus E, opposing EMF in the conductor in the coil according to the Faraday's law of electromagnetic induction. Thus, voltage can be obtained at the terminals labeled A and B. Okay, so this is how we can explain this phenomenon. Then part 2, it says, as the mass falls, the student connects a wire between points A and B, shown in figure 10.3. He notices that mass takes a longer time to connect when the wire is connected. The student suggests that this is example of Lenz's law, state Lenz's law, and suggest why mass takes longer time to fall. So first of all, Lenz's law it states that the induced current flows in a direction that opposes the cause producing it. Okay, this is how, what Lenz's law states. So remember what is happening. So when we connect this a wire between A and B, the current starts flowing in the coil. Okay, so because the potential difference is there, so the current starts flowing in the wire. So this becomes for example, a current carrying conductor, and that if a current carrying conductor is placed inside a magnetic field, that current carrying conductor faces a or experiences a force, and this force is you can say is in such a direction that opposes the cause that is producing this force. So technically what will happen is that if this force slows down the coil motion, and also uh, the with the passage of current in the coil becomes magnetized, and um, uh, and when it becomes magnetized, uh, the north pole, and it becomes either attracted towards the north or towards the poles, or it becomes repelled by the poles depending upon the you can say direction of the current. And in this case it also slows down the motion of the uh, overall coil. And this is the phenomena that is happening over here. So let's write it down. uh, so I'll start this here. So when the wire is connected uh, between A and B, the current starts flowing in the coil. The current carrying conductor in a magnetic field experiences a force. This force is opposite to the cause producing it, according to the Lenz's law. Seeing it, this causes the or the, or you can say this causes this this force slows down the motion of the mass, and it takes longer time to fall. Also, the coil becomes magnetized and is attracted or repelled by the poles of the magnet, resulting in slowing down of the motion of the mass. Okay, so this is how you can explain this phenomena. However, if you are going to omit the last part, that when that says that when your coil becomes magnetized and it either attracts or repelled by the poles of the magnet, resulting in slowing down the motion of the mass, you can also you can easily skip this part, because this actually is not directly related to the Lenz law, which they are asking us from here. So so your marking scheme states that uh, explain the Lenz's law 1 point, then uh, determining then for 2 points for the explanation of the uh, that why a current that the current carrying conductor in a magnetic field experiences a force, and this force is equal and opposite in direction to the cause that is producing it. And that is the 2 points which are which are required by the examiners to give you complete credit for this part. So this is all from this exam, and I hope you are able to understand from this video. And overall, I wish you all the best for your exams and for your future endeavors. Thank you for listening. Take care. Bye bye.